For this artifact, we're demonstrating if it is possible to use the tracking of an operator's heart rate and the deviation of their heart rate over time as an accurate method of being able to make decisions within computer systems. So the components of this artifact are 3 nunchucks in serial, 3 Arduinos in serial. We have one which is taking the information from a physical control device which is operated by the operator. In this case it's a Wii nunchuck, which is being communicated over I2C. That data is being interpreted and is being passed over to our data fusion Arduino here, which is taking the information from the operator through a polar T31 non-coded ECG heart rate monitor, which is wirelessly transmitting to a polar transcoder, which is interpreting the data, and as this device, this Arduino here, is polling the data and is receiving it over a serial connection, and it performs, given the data from the nunchuck and from the heart rate monitor, we have some decision logic being conducted here, depending on the heart rate, how it changes over time, and the deviation that is occurring, and is being converted to a instruction which we can create a HTTP payload, which we're then transmitting over TCP/IP to our wireless router, which is being then transmitted to this Wowie Rovio, which is a roving robot. So, utilising the heart rate monitor, every time the heart rate monitor detects a pulse in my chest using the ECG sensors, it will transmit its own pulse, which this transcoder will receive, and the status light will flash, meaning that there's new data being interpreted on this transceiver, which when we poll we'll be able to recover the data and be able to make inferences on the heart rate depending on the data stored on the chip. So for this demonstration we're using a data set where an operator was at the time conducting light to moderate exercise on an exercise bike, and it was found that with exercise being used as part of the test, that the going from a base heart rate of approximately 62, a resting heart rate, it produced a large deviation where the heart rate would max out at approximately 120. As a result, the decision boundaries that we used were larger, where our decision boundaries for restricting the use of the system progressively was at 20% intervals, where the average deviation over a rolling 5 sample set of data, as it increased at 20% intervals to the base heart rate that was recorded at the start, produced changes in data. So at the moment what it's doing is establishing a base heart rate over 10 readings to make sure it's stable. And then what we find is that as the heart rate changes, at the moment we have it at the heart rate staying at green, but as the heart rate is increasing, as it is now, we find that is the tracking deviation is at 40%, the system slows down progressively. So this individual, at the time of the recording, was starting to pedal faster on the exercise bike, and as his heart rate was increasing, the deviation away from the baseline was getting greater. And it was found that with our system, we could have systems, okay, and at this point our system is saying that the deviation's gone too great, so the system is not allowing us to use it at all. And now in the data set, the individual stops riding on the cycle, is now going into a recovery phase. It was found that obviously exercise produces a large variation, but we can have situations where change in heart rate could be quite subtle. For instance, having a shock video typically produced a maximum 20% deviation. Very, very light exercise, just moving legs, produced around approximately a 5% deviation. And as we see, as his recovery time is occurring, we're actually starting to get faster speeds. As we are starting to recover and get closer back to the base heart rate. Oops.